Hello everyone. So today we'll be solving a LeetCode harder problem. It is pretty hard. Candy. So the problem states that we are given like n children standing in a line, and each child is assigned a rating value which is given in the form of an integer array ratings. Okay. Now we need to give some candies to these children with the following requirements, such that each child must be given at least one candy, and children who has a higher rating get more candies than its neighbor. So for example, in this case, if we have a children whose rating is 2 and a children whose ratings are 1, so this is a child whose rating is greater than both of its neighbors. So hence, if these childs are given candies x and y, it should get candies z which is greater than x, means x and y, means it should be greater than both. Okay, so we need to assign the candies in such a order that children with a higher rating get more candies than its neighbors. And now we need to assign candies in such a way such that we are distributing the candies to the children satisfying the given requirements, as well as the number of candies given is minimum. So we need to minimize the number of candies that we need to give. So for example, if we have this as a given input 1, then we have 0 here, then we have 2. So we know like this children has a rating greater than this. So we need to give this child a candy greater than the number of candies given to him. So since it is lying at a bottom point, so let's try to give him candy 1. So then it is sure that this should get a candy which is greater than 1, and since we need to minimize the number of candies, so let's give him 2 candies. Okay, then and for 2 we also see like it is greater than its neighbors, its rating is greater than its neighbors 0, 2 is greater than 0, so we also need to give him candies greater than 1, so hence we give him 2 candies as well. Now we see for each child the conditions requirement are satisfied. Each child has at least one candy, and children with a higher rating gets more candies than its neighbors. Here 1 was greater than 0, so here he has 2 candies, here he has 1 candy. Here again 2 was greater than 0, so here he is given 2 candies and he is given 1 candy. So how many candies we need to distribute? We distributed 2 plus 1 plus 2 equals to 5 candies. And this is the means the optimal output here. Like we cannot satisfy the condition by distributing less than 5 candies here. Okay, let's try a different input. So we have 1, then we have 2 and 2. Now again this 2 is greater than 1, and since 1 is lying at the bottom, so let's try to give him 1 candy. Now this children should get a candy greater than 1, so it should get 2 candies. Okay, now we see that this child's rating is means equals to its neighbor, hence it is not greater than its neighbor. So even if we give 1 candy to him, the conditions will still be satisfied. What are the conditions? Each child must have at least 1 candy, and children with a higher rating get more candies than its neighbors. So we see like this child has a greater rating than its neighbors, one of the neighbors, so it is getting a greater candy than the neighbor from which it has a greater rating. And for this child, it does not have any neighbor from which his rating is greater. So you can simply give him 1 candy only, and everything conditions are still satisfied. And we how many candies we gave? 1 plus 2 plus 1 equals to 4, which is the optimal output here. So like how can we try to solve this problem given the ratings? So we need to like satisfy 2 conditions. Okay, we need to satisfy 2 conditions. If ratings of I is greater than ratings of I minus 1, means it, suppose it has a rating x, then it will have a rating y. So ratings of I is greater than ratings of I minus 1. So we need to make sure that candies given to I should be greater than candies given to I minus 1. This should be satisfied. Okay, and if we have ratings of I greater than ratings of I plus 1, then that means suppose it was z, so y is greater than z, means for rating I it is greater than rating of I plus 1. So we need to make sure that the number of candies given to I is greater than the number of candies given to I plus 1 actually. So we need to make sure this as well. So what do we need to make sure? Like if both the conditions are satisfied, like ratings of I is greater than ratings of I minus 1, and ratings of I is greater than ratings of I plus 1, then that means candies of I should be greater than both of these two values. And if it is greater than both of these two values, it simply means that it should be greater than max of both, right? Max of candies of I minus 1, comma, candies of I plus 1, right? This should be satisfied to like means give the candies. Now if only one of the situations is satisfied, then only one of the relations we need to satisfy. So how can we like approach this problem? Now we see like if we try to means give candies in a random manner, then suppose we give one candy, then two candy, then three candy, then the next one ratings is smaller, so again we gave him two candies, then one candies, then suppose it again has a smaller, so we cannot give him zero candies, right? So now this assignment was bad. We at least need to give this person one candy, then give this two, then three, then four, and this does not need to change. Then if the ratings were in the form of this, the slopes were in the form of this, then means giving candies in this manner was good. So we know like means assigning candies in a random fashion is not feasible because we need to satisfy two conditions at a time. Okay, so means apart from like satisfying two conditions at a time, let's try to only satisfy a single condition at a time. Only try to satisfy a single condition at a time. So just the condition of ratings of I greater than ratings of I minus 1. Suppose we just need to simply satisfy this condition. So what will means how will be distributing the candies? Let's give one candy to the first child. Okay, we have given one candy to the first child. Now we see like 3 is greater than 1. Hence we need to give this child more candies than I minus 1. So let's give him two candies. Okay, one more than the previous. Then again we see ratings of 4 means 4 is greater than 3. So again we need to give this child more candies than the previous one. So we give him one more. So we give 3 candies. Now again we see this rating is greater than 4. So we need to give him one more candy. So we give this 4 candies. Okay. And now we see like this 2 is less than 5. Means this condition is not satisfied. 2 is not greater than 5. So hence we do not need to give this child 5 candies. So what we can do is we can simply give him one candy. Then only the condition will be means for left these conditions will be satisfied. We do not need to check for the right property now. We just are checking for if I is greater than I minus. If I is greater than I minus. In that case, we are simply assigning in this manner such that this condition is not violated by the candy. Okay, so this is the left part. Now what about the right part? Like if ratings of I is greater than rating of I plus 1. So if ratings of I is greater than ratings of I plus 1, that means we need to start distributing the candies from the end. So that if the current rating is greater, then if this was given X candy, we can give him X plus 1 candies. Okay, so let's try to satisfy this. So we give means initially we give the first person one candy. Okay, now how do we satisfy? We move up. We see this 5 is greater than 2. Hence we will give him one more candy. So we give him 2 candies. Okay. Now we see this 4 is not greater than 5. So this condition will not be violated even if like we give us means as minimum candy as possible. So we will give him one candy. Again we see this 3 is not greater than 4. So we'll give them as minimum as possible so that this condition is not violated. So 1. Again we see 1 is not greater than 3. So we give him one candy as well. For right we got this. So for just satisfying the left conditions and the right conditions alone, we got these many candies that we need to give. Now what will be the case? If both of the conditions are violated, then how many candies we need to give? We need to give max of both. Right? Max of candies of I minus 1 and max of candies of I plus 1. That means if we want to satisfy both the conditions at a time, we should be means satisfying the stricter constraints first. For example, if x is greater than 3 and x is greater than 2, then that means x should be greater than 3, right? Because these many candies should be given, x should be greater than 3. It means the constraints which are more stricter should be satisfied first. That means if for left we need to give him 4 candies, then giving him 2 candies is not feasible. We need to satisfy the stricter constraint. Here 4 was greater than 2, so hence we need to satisfy this stricter constraint. So what do we observe? We can observe like to satisfy both conditions at once, we need to satisfy the stricter constraints on candies. And how will the stricter constraint be satisfied? If x is greater than 3 and x is greater than 2, then we will simply be taking the max of them to satisfy the stricter one. Okay, so what do we need to do? We need to take max of left of I and right of I. So these many candies will be giving. So candies, how many will give? We will give 1, 2, max of 2 and 1, max of 3 and 1, 3, max of 4 and 2, 4, and max of 1 and 1, 1. So as you can see, the number of candies that we need to give in this case is 1 plus 3, 3, 6, 4, 10, 11. Hence 11 is the minimum number of candies that we need to give to satisfy the ratings condition for this input. And how we did it? We just initially tried to satisfy the condition for the left, then tried to satisfy the condition from the right, and then at each step we tried to satisfy the stricter constraints, because we need to satisfy the stricter constraint first, then the less stricter constraint will already be satisfied. At each step we take the maximum so that both the constraints are satisfied. So this is the approach that we will be following to solve this problem. We try to like break it down into two smaller sub problems and try to see like how they will be related to each other. And this is why like how we'll be solving this. So let's see the code. So we first satisfy the conditions for the left. So initially we'll give the first candidate rating means one candy. Now we'll satisfy the conditions for as we move up the slope. So if rating of I is greater than rating of I minus 1, that means if this was given x, we'll give him x plus 1. So if this was given left of I minus 1, so left of I will be given left of I minus 1 plus 1. Okay. And then if any scenario this becomes a condition like this was given left of x, and this condition means it is not satisfied, like this is not greater than ratings of I is not greater than ratings of I minus 1. So we'll be giving a single one here. Okay. So this in this case we'll be giving left of I as 1. And now we'll try to satisfy the condition from the right. Okay. So we'll giving the rightmost one as 1 candy. Now if the condition is satisfied like ratings of I is greater than ratings of I minus 1, then we'll increase the right, means we'll giving this 2 candies. Then again if ratings of I is greater than ratings of I plus 1, then we'll give him 3 candies. So we'll increase right, and else right will become 1. Means instead of like creating a vector, we simply create a variable. And at each step what do you need to do? We simply need to update our sum with the max of left of I comma right of I. And currently the right of I will be denoting by this variable. So instead we can like also create a vector in right of n, and then first do this pre-computation and then do a separate loop to calculate these two values. Or we can like, since we are calculating right in a running fashion, so once the right value is calculated, we simply take the max at each step and update our sum. So this will be the complexity, means this will be the overall like approach to solve this problem, to like divide it into two sub problems of satisfying the left constraints and then the right constraints separately, and then to see how they are linked here. So as you can see, like this will be of the order of n, the time complexity, as well as the space complexity here is of the order of n. And as here the constraints were till 2e4, so this will get accepted here. So let's try to submit this code. So yeah, this is the same code that we wrote, and instead of creating a separate vector right, we created this. So as you can see, like it runs in 0ms, which is fine because we are just iterating through the array twice only. Now like can we further optimize it? like is further optimization possible here. So as we know, like we will definitely need to iterate through the array once. Hence, time complexity cannot be further optimized. But as you can see, like we are using this extra big of n space here. So can we optimize this space to something of the constant time? So let's try to analyze how, like whether it is possible or not, and how we'll be transitioning from this left right to like a constant space complexity solution. So suppose we are given the ratings array, right? We are given the ratings array. Now what do we need to do? We'll have the ratings array in some form of, like suppose we have the increasing slope, then we'll have the values decreasing, then suppose increasing, then decreasing, then suppose we have a flat to flat, then decreasing, then increasing, right? Then suppose increasing, then plateau, then increasing. Suppose, so these ratings can be in will be in the form of slopes only, right? First, for some sequence means for some part it will be increasing, then it will be decreasing, then it may remain same. For example, it was the ratings were of the value like 10, then 11, then it became 8, then again it became 13, then it became 12, 12, then became 11, then became 15. So for example, 14, then 13, 13, 18. Okay, so suppose this was the ratings array that was given. Now we need to assign candies in some fashion. So how will be assigning candies? So let's see, like suppose we have a increasing slope. Okay, we have a increasing slope. So we want to assign candies in the minimum possible fashion, right? So we'll be assigning candies in what manner? We'll be assigning candies 1, then 2, then 3, then 4, till the length of this row. Suppose it is k. Okay, so we assign candies in this fashion. Now suppose it starts decreasing. Okay, it starts decreasing. So we need to know like how we'll be assigning it. So we need to start from here, the bottom point. After it was assigning, suppose so we have 1, we have 2, 3, 4, 5, 6, so on, and then it will say like we need a new value for this, which is k2. Okay, this is what you need to do. Means we'll be assigning values from 1 till k2 minus 1. This is fixed. Okay, and here 1 till k1 minus 1 is fixed. Now for the peak value that we have two values, either k1 or k2. Now we need to means assign the more stricter constraint first, right? So obviously which will assign at the peak will assign the value k1 max of k1 comma k2. So what will be the assigning of value? It will be 1 till k1 minus 1, then 1 till k2 minus 1, and then max of k1 k2. So like one thing we can do is we get information about these peaks, means we store the information about these dips that we have, and then we start from these dips to means fill the values. Okay, this is maybe we can follow this approach. But we'll know like if we are storing the dips, then again we'll be requiring some space to store it. Okay, so we'll not be able to do it in like constant space. So how can we do it in a running fashion? Like how can we do it in a running fashion? So to do it in a running fashion, what we can do is, suppose we just like to satisfy the condition for this left peak only. Okay, then we see like how the values will be changed. Let's try to assign the values. Suppose we had the increasing peak. We started from like peak equals to 1. Okay, and they gave till 1, 2, 3 till this peak value. Okay, so the sum increased by peak into peak plus 1 by 2, means 1 plus 2 plus 3 plus dot 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 peak. Suppose these many values we have already assigned. Now we encounter a downward slope. Okay, so how will we be assigning it? Now we see like going in the forward direction once to identify this dip, and then going back to fill the values. Maybe either we can do it, or we can simply observe that since we'll definitely be assigning values from 1 till k2 minus 1, right? We'll definitely be assigning values. So since we do not need to return the manner in which we are means assigning the values, We only need to return the sum, right? So what if we again start from 1 here? Okay, so 1, 2, 3, 4. So we start from down equals to 1 and we keep assigning till what? Down minus 1. Okay, because we need to fill till k2 minus 1, right? Now what we have done here is we have filled values from 1 till peak and plus 1 till down minus 1. Now for this peak part, what did we needed? We needed the value as max of k1 comma k2. That means we needed the value as max of peak comma down. Right? We needed the value as max of peak comma down. But we have already assigned peak value to it. Hence, if this down value was needed to be assigned, then we need to update this peak with down. So how many extra do we need to assign? We need to assign sum plus equals to how many extra candies we need to give? We need to give down minus peak. Okay. So how did we solved it? We solved it using, when we encountered an increasing slope, we simply assigned values from 1. We increase the peak till it is possible. And the sum value will be increasing by peak into peak plus 1 by 2 because 1 to sum till peak. Now, if we encounter a decreasing slope, we'll keep moving through the decreasing slope till it is possible and find out this down value. And now we'll assign the values till, means 1 plus 2 plus till down minus 1. Now what do we need to do? We have covered the increasing slope as well as the decreasing slope. Now for the peak, we need to see if this down value, means here we are writing it in reverse fashion, but real was this. So we need to see if this k2 was greater than k1. Then this max of k1, k2 will be k2, right? So hence we need to see whether we need to assign k2 or not, whether assigning peak was sufficient or not. If this down value is greater than peak, then we need to update this peak with down. So how many extra candies we need to give? It will be simply the difference of down minus 1. So in this case, we will be updating it with this. Now again, we'll see we'll have assigned values in this form. Now again, we'll get some increasing slope. So again, in the next iteration, we'll check for the increasing slope, then the decreasing slope, and update the value in a similar fashion. Okay. So at a time, we'll be solving in pairs, in form of pairs of increasing slope and decreasing slope. Now you might think what about the case where we have plateaus? Either the plateau is of the form of this or the plateau is form of this. What we'll be doing in this case? We simply know this means this candy will already have satisfied the peak requirement, right? So we can simply give this one candy and then again we'll have a new peak. Okay. Or we know we'll have given this one max of peak comma down. Okay, max of peak comma down. We'll have given this one this value. So we'll simply give this one value and again we will have a down slope. Okay, so we'll give values from 1 till down. This is what the approach will be following. If we have a plateau, we'll simply assign this one value and then move forward to calculate the values for the peak. So this is the approach to solve it in form of pairs of we'll keep each pair of p means increasing slope and decreasing slope in the form of pairs and we'll solve it. And hence here we'll be able to solve it with constant space. I hope you are able to get the logic of how we are simply assigning in a running fashion and then update the value at the peak to see whether the downward slope was greater or not. If it was greater, then we'll simply update the peak. So let's see the code for this approach and then we'll be able to understand it better. So what do we need to do? Initially we have some value. Okay. So since we need to, at each step we need to check for I and I minus 1. whether ratings of I is greater than I minus 1 or ratings of I was less than I minus 1. At each step we need to check this, right? So for I equals to 0, we simply assign what? Candy 1 and sum is initially 1. So initially we assign our sum by 1 and we will now start the loop from the first index. So that this I minus 1 exists and we do not need to separately check for it. Now we'll keep solving for the iteration in form of pairs. We'll do this while loop till it is end and we'll solve it in pairs while means increasing and decreasing. So first we need to see whether the current I is in the form of plateau, means this value is the same as this. That means we'll assign one candy here. So we'll simply increase our sum by 1. And now after that there may exist some peak and then down peak. So we'll simply increase the height, then it will be handled separately. So for plateaus we'll simply assign the cost value. Suppose it was again 1, again a peak was there. So again we'll assign it value 1 and then try to solve for the remaining part. Okay. So if it is same as the previous value, means it is a form of part of a plateau, we'll assign it 1 candy, means increase sum by 1 and move I to the next rating or the next child. Now we'll be solving it in the form of pairs. So how will be solving it? We know, like for this peak we have already given, means the down value is already allocated, means this value was already allocated either to I equals to 0 or in the form of plateaus, right? So if this one value is already allocated, so for I will pointing be here currently. This means if ratings of I is greater than ratings of I minus 1, so we'll need to start our peak with 2, means first add value 2 here. So at each step we'll first increase the peak. So this will from 1 it will make the peak as 2 and then we'll assign, means increase sum by peak. So it will add 2 value. Now for next I we'll have the peak as currently it is 2, so it will be increased to 3. Then it will be added and so on till peak. Okay, so this makes sure that since we are increasing peak before and then we end, so this makes sure that we are knowing that peak, the value represented by this peak will be the value which will be present at the top of the slope. Okay, now we need to account the downward slope. How will be accounting the downward slope? So we need to fill values in the form like 1, 2 till down minus 1. Right? So how will we be filling it? We will be filling it in the form of, we start down from 1 and we need to check whether ratings of I is less than ratings of I minus 1. So we'll keep doing this while ratings of I is less than rating of I minus 1. So here we need to add 1 only first, then increase. Then for the next iteration we'll add 2. Then for the next iteration we will add 3 and so on till down minus 1. And in the end the value will come down minus 1 plus 1, which means down. So this will be the value which will check with the peak value. Since we have assigned values from 1 till down minus 1. Okay, increased means added in our sum, and now the final value of down will be down, and now we need to check whether the new down value that we have is greater than this peak or not. If it is greater than this peak, then we will simply update this peak with the down and hence increase our sum by a difference of down minus peak, which is simply sum plus equals to down minus peak. So this is the approach. It is the same as we remove the peak part and we increase the down part. Okay, so we just replace the peak part with the down part. Now you might wonder, like, what if initially only the slope was downward, or in the end the slope was increasing and no decreasing part was there, means only one of these things got executed. What about that case? So we know, like, even if if it was the last part, so this peak value that we have will definitely be greater than 1, right? Because this peak value will be increased to 2. So at minimum this value will become 2, and this down that we have is 1 only, and then this thing will not get executed because we do not have a downward loop forward, because the rating is array ending in the form of this. So this condition will never be executed, and hence this subproblem will be solved separately, like 1 till peak. This will be solved separately. So this down part will never get executed. And similarly, if we have only a down part and no increasing part after that, means there was no increasing part in the start. It started with a downfall only. So what we'll do, we know like this peak will be 1 only. So we have assigned this peak as value 1. Okay, and now we'll keep assigning till 1 till down minus 1. So the peak will remain 1 only, and the new value will become down, and which will be definitely be, this down will definitely be if it is greater than peak. So we'll replace this one with the down value. So replace this one with down value so that the downward slope condition is satisfied. As we can see, this means handles both the cases. If they are existing in pair, means that if the slopes are existing in the form of pairs, or if only a single slope is present at the end, or if the ratings function start with a downward slope. So it will be handling both the cases. And as you can see, we did not use any space to store any extra information or pre-compute any extra information. Hence, this will be the big of n time complexity and a constant space complexity. This is the solution for this problem. Let's try to submit the code. So initially, as you can see, like it beats 55% of the space. Now let's try to submit and see how much space it took. As you can see, like it beats 92%, means it beats most of the solution. So I hope like you were able to follow how we like tried to analyze the slope of the ratings array that we are given, and then like try to fill the problems in a greedy fashion, and then try to analyze how this, if the downward slope is greater, how we'll be updating the value at the peak. So this was the overall means approach for this problem. I hope like you were able to grasp both the approaches of using means satisfying one condition at once using left and right vector, and then we moved on to the constant space one. So I hope like you were able to like grasp it, and you will be able to use this slopes kind of thing in similar problems in future. And if you did, like please make sure to like the video, and if you have yet any doubts remaining, feel free to comment down and I will be happy to respond. Thank you so much for watching.